To RSLogix 5000, course number 3. This is a ControlLogix Programmable Logic Controller. My name is Vincent Wedlick, and this is the third of a series of courses. This is the basic RSLogix courses that Alan Bradley teaches. They cover a lot of the same ideas. I've added some digital logic information for the people that need to take the EIT exam, the Engineering and Training or Fundamental Engineering exam, before the PE exam. So if you were to watch the RSLogix 500 1, 2, and 3 and the RSLogix 5000 1, 2, and 3 and you understood and worked through all the homework problems, you would do very well on the digital and computer logic sections of the fundamental engineering exam. Credits for the course, obviously RSLogix 5000 version 15 and the demo version 16 were used, as well as RSLinks Classic. Alan Bradley Online Manuals, www.ab.com. Register yourself as a user and get the latest manuals and demo software. You can actually go online and download the 90-day demo software, and you'll notice when you go to the help screen, you'll see online books and online manuals, and I've just provided them for you for the CD for people that don't have a high-speed internet access, but you can download those, and I encourage you to, because I may or may not have the latest version. Again, this is just for tutorial reasons, not for actual control. So if you're designing a panel for a client, you want to make sure you have the latest stuff, the latest manuals, the latest installation guidelines, etc. I also used Wikipedia. It's a good resource. I used a little bit of an instrumentation and control section from some company in Shanghai. I just touched on it. It's really ISA logic diagram, or the ISA symbology for flow diagrams or piping and instrumentation diagrams. And I encourage you to really study your instrumentation and controls, because what will happen is you'll have to deal with process engineers, or you might be a process engineer, and you'll draw these different ISA symbols, and these symbols actually tell us programmers how to make the program and how to design the control panel. I also used some ideas from MIT OpenCourseWare, the MIT Online. I encourage you to go there. They've got some excellent course on electrical engineering stuff on there. You can get stuck in there for a couple of years, I think. And then, of course, I've personally been programming for over 16 years, so you will get my personal insights as well. Course prerequisites. It is recommended that you complete the RSLogix 500 PLC Course 1, 2, and 3. This is not a 100% requirement. You don't have to do it. It just would help you. And I think that it provides a very strong fundamental starting point for PLC programmers, and then obviously the RSLogix 5 and 5000 is somewhat more advanced. I haven't offered the 5 RSLogix 5 courses yet. Probably will do that because they haven't gone away, even though you thought they would. They never have. So this course assumes you have completed RSLogix 5000 course 1 and 2. And then, of course, you finished all the homework, because that's the key. You've got to do the homework, and you've got to practice these different problems. What we're going to cover, the course overview for RSLogix 5000 is first we'll do the RSLogix 5000 PLC number 2 homework review. We'll cover all those problems. Then we'll do JK flip-flops and examples using RSLogix 5000. And if you noticed in RSLogix PLC number 2, I gave you a JK flip-flop problem as well as a T flip-flop problem. We'll go into a little bit more detail on the T flip-flops and examples using RSLogix 5000. And again, the JK flip-flop, T flip-flop, Karnoff maps, that's all really for the fundamental engineering exam. But it's really good that you understand how to program these, because you can take real-world examples, logical examples, and easily convert them over into ladder logic programs. And that's when you can do that. Well, you can take AND gates, OR gates, exclusive OR gates, even flip-flops, the ideas behind flip-flops, and convert them over into logic. That's when you start to be able to take processes and convert those into code as well. It's real important that you understand that. We'll cover the T flip-flops, and then we'll cover just touch on the Karnoff mapping using the RSLogix 5000, because we did cover Karnoff mapping extensively, and I believe that was RSLogix 500 number 2. So then we'll get into programming basic instructions using RSLogix 5000, compute, math, move instructions. Then we'll touch again on monitoring and editing tags using RSLogix 5000. Then we'll go into forcing and toggling bits using RSLogix 5000. Some of these ideas you've probably seen me do as I go along. You know, I'll turn or toggle a bit or force something on, or I'll start monitoring a tag. But you know, we'll talk a little bit more about it and play with it a little bit more. Next, we'll go over troubleshooting controller problems, and I'll do a little focus on the faults, because what will happen on these PLCs is you will just get a fault and it'll shut your entire process down. It all depends on is that a problem for you. I mean, if usually what I do is I don't do anything with it. I just make sure that I don't fault the PLC. There's certain things you can't plan for, like an I/O card going bad or something like that. There's certain things you just don't want to do. Some of those items are you're downloading the PLC, you're in, you know, remote mode or program mode, and somebody flips the switch to run mode right when you're downloading. Well, that'll create a fault. You don't want to do things like that. So then we'll go over configuring the analog cards and setting up a PID instruction. So we haven't touched on that yet, the PID instruction. We might have dropped an instruction in, but we haven't actually talked about what a PID is, a proportional integral and derivative control loop. So we will actually set up a PID loop, and then we'll talk about it, and then we'll kind of go through a little simulation of one of the loops. Then we'll talk about ISA symbols and examples using RSLogix 5000. The ISA symbol library, you can actually go to the ISA symbol, you know, the ISA Society, I guess it is, and they have these books and things that you can buy off the internet. And you need to read them, and you need to understand them. If you're going to work in this process, you know, process engineers and what have you, you need to understand what the symbols that they use to convey their ideas to build, machines and to program as well. And then during the entire portion of the course, I'll be drafting ladder logic for an RSLogix 5000 projects. So you'll get more hands-on there as well, and I encourage you to follow along. Okay, so next we'll go right into the homework. So we'll move through the homework problems from course number 2 first, then we'll move on to the new items. Okay, the first problem was somewhat easy. It was write a ladder logic diagram of the following. If 1 or 2 or 3 is true, then output coil 4 turns on. And that's exactly the kind of words that somebody will tell you. They'll say, if this pump turns on or this valve opens, then do this, then start this motor or whatever. So when you listen to them, they're telling you the logic gates. 1 or 2, that's a logical OR. 2 or 3, that's a logical OR as well. So 1 is in, and you can see it right here, when you actually take these bits, 1 is ORed. It's got a branch ORed with, 1 is ORed with 2, 2 is ORed with 3. So if any one of these turn on, 4 will turn on. Next, we had if 1 and 2 are true, then turn on output coil 3. So again, this is the logical AND gate. It's 1 and 2 are required to turn on before 3 can turn on. The next one was somewhat of a trick question. If you haven't figured it out, I just used the homework from RSLogix 500, which was a good thing because it kind of brings out some differences between the two. When T4:1 is done, what bit turns on? Well, obviously T4:1 is a tag or a address scheme used in RSLogix 500. So you can't put in T4:1 in control logics, as we covered in the last course. But you can put in T4 underscore 1, or you can call it anything you want, timer 1, or, you know, as long as you stay within the rules that we covered before on what a tag can be and can't be. So what actually would be, you know, what bit would turn on? And that is, if you go into your tags and you look in your T4 underscore 1, you'll see that the .done bit would turn on when that timer times out. And that's not any different for the RSLogix 500 slicks. The T4:1.1 done bit would turn on as well. Next, I asked you to draw a truth table for a JK flip-flop, and there's different types of JK flip-flops out here. I picked right here a negative edge triggered JK flip-flop. So you can see this little dot, this is the inversion dot, and so that's a negative edge. This little arrow right here is the edge portion of it. So it looks at the falling edge of the pulse. So if the clock pulse right here, there's a stream of clock pulses coming in here. If it's a 0, if it's at the 0 point, then it doesn't matter what J or K does. They can be 1 or 0. If it's a 0, nothing happens, and there's no change. If it's sitting there at a 1, you know, binary on off, 0 being off, 1 being on, then it doesn't matter what a JK does as well. There's no change on Q. If it's at the rising edge, so as the pulse comes up, it's rising edge. It goes from 0 rising edge to 1. Nothing happens because this is a negative edge triggered JK flip flop as opposed to a rising edge. And then if the clock doesn't matter, if J and K are 0, if that's a 0 and that's a 0, it doesn't matter what the clock pulse is doing. If it's rising, it's a 1, or it's falling, it's not going to make any change out here because J and K are 0. However, on the falling edge of the clock pulse, if J is a 0 and K is a 1, then Q will be a 0. So if J is a 1 and K is a 0, and you're cruising through your clock pulse here and you fall down the edge, the negative edge, at that point where it's coming down the negative edge, the Q will go to 0. So, and then if, that would be if J is a 0 and K is a 1, then Q would be a 0. And then if J is a 1 and K is a 0, then Q would go 1. And so then you have a falling edge. It'll toggle if J and K are 1s, then every time it goes on a falling edge, it'll just toggle. Q will just toggle on and off, and that's how that works. You might ask, why would you even need a JK flip-flop? And really, it's because you want to save a bit. It's a type of memory address. I think we kind of covered on this previously. So then I asked you to draw a JK flip-flop in RSLogix. And what we're going to do is later in this course, we're going to actually do that. We're going to take another type of JK flip-flop. We're going to convert it into ands and ors or nands or whatever. And then we're going to take that information and convert that directly into RSLogix. The next problem was draw a truth table for a T flip-flop. And so I picked randomly a non-clock T flip-flop. The next state of Q positive will be a 1 if the present state Q is a 1 and no T pulse occurs, or the present state is 0 and a T pulse occurs. So let's look at this again. There's no clock. It's a T flip-flop. T is toggle. The next state of Q plus, will be a 1, if the present state of Q is a 1, so here you've got a 1 here, and there's no T pulse. So here you have a 1, there's no T pulse, so you're going to have a 1. Or if the present state is 0, and a T pulse occurs, then you'll get a 1. So that's how a T flip-flop works without a clock. Okay, next we'll look at a clocked T flip-flop, and we'll actually look at a clock pulse, if you will. You know, it's a stream of the clock pulse. So let's take a look at this. Again, this is a negative edged. So at times T2 and T4, T2 right here, so here's your clock pulse. It's going on and off, on and off, on and off. At times T2 and T4, the T input is a 1. So during this period and this period, you can see the T is actually a 1 right here, okay? So, and the flip-flop state Q changes. So Q actually changes a short time after the falling edge of the clock pulse. At times T1 and T3, the T input is a 0. So here you got your T input is a 0. And you can see this is the negative edge, the negative edge, the negative edge, and the negative edge. And the clock pulse did not change does not cause a change of state. So here at times T1 and T3, the T input is 0, and the clock pulse does not change the output state. So you had a positive clock pulse, but this was 0, so nothing happened here. You had a positive clock pulse here, and this is a 0. This was already a 1, so it just stays a 1. So that's how a toggle bit changes with a clock pulse or a T flip-flop. And next I asked you to draw a T flip-flop in ladder logic, and again we're going to cover this later in this course and actually go through that. The next problem was decimal to binary. 727.25 decimal equals what binary? So first let's break this problem up into two pieces. We have the 727 over here, and we have the decimal 0.25 over here. So because it's a binary, we're trying to convert to a binary number. We're going to divide by 2. Remember, binary is 2, octals 8, hexadecimal is 16. So hex, if this was decimal to hex, we'd divide by 16. But it's binary. So we take 727 divided by 2 equals 363 with a remainder of 0.5 or 1/2. So this is the lowest significant bit here. Remainder is 1. Then we take this number right here. 363 divided by 2 equals 181. 0.5, remainder half, so we have a remainder 1. 181, again this is 181 divided by 2 is 90 with a remainder of a half, so we put a 1 here. 90 divided by 2 is 45 with no remainder, so we put a 0 there. 45 divided by 2 is 22 with a remainder half, so we put a 1 here. 22 divided by 2 is 11, so there's no remainder, so we put a 0 here. 11 divided by 2 is 5 with a remainder of a half, so you got the remainder is 1. 5 divided by 2 is 2, remainder half, so you have a 1 here. And 2 divided by 2 is 1, no remainder, so you put a 0 here. And then obviously it's 1 divided by 2 is a 1 here. So this is on the most significant bit on the bottom, least significant bit on the top. So you just fill it in. So 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1. Next we'll move over to the decimal side. So instead of dividing by 2 on the decimal side, you multiply times 2. So 0.25 times 2 equals 0.5. So it hadn't gone above 1, so it's 0. And then you have 0.5 times 2 is 1 with a remainder, so you'd put a 1 there. So here you have the most significant bit is on the top. You can see the least significant bit is here on the top. The most significant bit is on the top of this one. So you have 0.0, 0.01. Next problem is 123.17 decimal equals what binary? 123 divided by 2 equals 61 with a remainder 1/2. So again, we have our r equals 1 here. 61 divided by 2 is 30, remainder 1. 30 divided by 2 is 15, remainder 0. 15 divided by 2 is 7, remainder 1/2, so you put a 1 there. 7 divided by 2 is 3, remainder 1/2, so you put a 1 here. 3 divided by 2 is 1, remainder 1/2, you put a 1 here. and 1/2 is, you put your remainder here. So again, you have your lowest significant bit at the top and your most significant bit at the bottom. So here you put 1, you got 1, 2, 3, 4, 1, 2, 3, 4, a 0, and then 1, 2, 1, 2 there. So now next we'll do the next side. So 0.17 times 2 equals 0.34, remainder 0. 0.34 times 2 equals 0.68, remainder 0. 0.68 times 2 equals 1.36. So there's your 1. That's where that comes from. So that leaves us with 0.36. 0.36 times 2 is 0.72. 0. 0.72 times 2 equals 1.44, remainder 1. So again, this most significant bit is on the top here, and the least significant bit is at the bottom. So this is 0.00101. 0.00101. I hope this is the last one. 356 decimal equals what binary? 356 divided by 2 is 178, remainder 0. 178 divided by 2 is 89, remainder 0. 89 divided by 2 is 44, remainder 1/2. So you put a 1 here. 44 divided by 2 is 22, remainder 0. 22 divided by 2 is 11, remainder 1/2. So you put a 1 there. And then you got 11. The 11 divided by 2 is 5, remainder 1/2. You put the 1 there. 5 divided by 2 is 2, remainder 1/2. You put a 1 right there. 2 divided by 2 is 1, 0. 1/2. You put the 1 there, and that's your word. 1, 0, 1, 2, 3. 1, 0, 1, 2, 3, 0. 1, 0, 0. Next, we'll do the decimal side, 0.89 decimal. So we have 0.89 times 2 is 1.78. Bring that 1 over here. That's your most significant bit. That leaves us with 0.78. 0.78 times 2 equals 1.56. Bring the 1 over there. 0.56 times 2 is 1.12. Remainder 1. So we could continue this, but we'll just stop. Otherwise we might never stop. Continue on forever. So we have 0.111. Next we have simplify. AD plus not BCD plus not BCE. Note not B equals not B, or B with a not on the top. In RSLogix 500 we kind of went over this and we solved it using the distributive and commutative identity solutions. And you could just kind of look at these different problems, and actually if you're actually taking the exam, you'll actually have the book with you. The little solutions book. I know they allow that in the state of Texas, so you can actually have some cumulative properties next to you, and you can probably derive the answer from that. But we're going to use RSLogix 5000 and take a different look at this. So AD plus not BCD plus not BCE, and so what you can do is you can look at this and you can factor out the D's. You see that? And that's what they've done. D, A plus not B, C. And then you can actually combine these within them, and then you have D, A plus not B, because you have a not B here and a not B here, and it was C or with E. And that's the key here. Remember that when you see the positive sign, that's OR. When they're multiplied together like that, that's an AND gate. So A is ANDed with D, ORed with not B, ANDed with C, ANDed with D, ORed with not B, ANDed with C, ANDed with E. That's exactly how that reads, and that's the logical problem there. So you can see that you could turn this into a ladder logic program fairly easy, and we'll do that. So here, what we're going to do is we're not going to go all the way through and break it all the way up, but we're going to try and reduce some of the number of inputs. You have 1, 2, 3, 4, 5, 6, 7, 8 inputs to get the output, right? So you have A is ANDed with D. A is ANDed with D. ORed with right here, not BCD. ORed with not BCE. Just looking at this problem, you can see that you've got some common instruction, not B. So you immediately just take that out. Just put the not B here, C, D, C, E, and there you can see a reduction as well. So Here you have A, D, not B, and it was C, ORed with D, E. So you have A, D, ORed with, this is ORed with, not B, and it was C, and it with D, ORed with E, equals out. So you can see you can take a fairly complicated, Boolean expression, and just using ladder logic, kind of figure it out. So you don't have to remember all the identities or all the different rules. Just kind of look at it in ladder logic and try to reduce the, some of the inputs, and you'll come to the simplified version of that. Draw the combinational logic gates for the following expression: A, not B, ORed with C. And again, these are our truth tables for the OR gate and the AND gate. And the OR gate is any one in gives you a 1 out. So if you have 2 zeros in, you get a 0 out. The AND gate is you must have 2 ones in to get a 1 out. So we're going to draw this in a combinational gates for the following expression. A is ANDed with not B, ORed with C. So here we have the AND instruction, or the AND gate. So you have A is ANDed with not B. There's your inversion, so that's the not portion of B. And the results of this is ORed. This is ORed with C, and that gives you an output. And the way you would draw that in ladder logic is simply A is ANDed with not B, ORed with C, gives you your output. So these homework problems shouldn't have been very hard for you. You should have been able to whip right through them fairly quickly. Draw the combinational logic gates for the following expression: A ANDed with C, ORed with D, and then this whole expression right here is not. Put a not right on top of it. ORed with BE. So we'll kind of just take this a little at a time. C is ORed with D. C is ORed with D. And then these two are ANDed together with A. See this? See the results of this OR gate right here is ANDed with A right there. And then this whole thing is inverted. So we put a inversion right there. And then we have an OR gate. ORed with, this is an AND gate. B is ANDed with E. B is ANDed with E. And the results come together, and then they're ORed with this over here, and then you get your output. So that's how you would actually do a combinational gate diagram. And you can see I use blocks in here instead of the actual symbols that we saw earlier. And the reason I did that is because a lot of times you have ISA binary logic diagrams. They'll ask you for that in a contract. They'll say, I want an ISA binary logic diagram. And what they mean is these are ISA type symbols instead of the conventional gates that you see in electronics. Next, we have simplify the following equation. XY is X and X ANDed with Y, ORed with not X, Y, ANDed with Y, ORed with Y, ANDed with Z. So again, looking at our Boolean identities, and I think I included one of those with each homework, you can see the solution fairly quickly, because what you do is you see X is ORed with not X. Whenever you see X is ORed with not X, that equals 1, so it just goes away. And then you're left with Y ORed with Y. A Y ORed with Y is just simply a Y. So then next you have Y ORed with Y, Z, and again a Y ORed with Y again is just a Y. So you end up with just YZ or ZY. Okay, so now we're going to show this in a ladder logic format. So we've got this rather long one here. You've got X ANDed with Y, ORed with not X ANDed with Y, ORed with Y ANDed with Z, and that's the results. And you can see the solution here, because it doesn't matter what X does. X could be on or off, because it really only matters what Y is doing in these two states. So these can actually cancel out, and you're left with Y and Z in series. So that's the solution. Okay, now let's talk about the K-map, the Karnaugh map. And the Karnaugh map is used to take a truth table and then convert it into a Karnaugh map and then simplify the equation using the Karnaugh map. And again, we covered this really a lot in RSLogix 500, course number 2, and we went over all the different maps, the 2 quadrant, the 4 quads, all these different maps, all the different variables. See, here we only have 2 variables. We have a P and a Q, but you can have up to 5 variables, and these maps get quite complex. If you really want to understand it, you want to go over that RSLogix 500 again if you've purchased the course. So here's our truth table, P 00011011, and if 00 is a 1, 01 is a 1, 10 is a 0, and a 11 is a 1, what that means is if P is a 0 and Q is a 0, then the output of this black box, if you will be a 1. Okay? And if P coming into it is a 0 and Q coming into this black box is a 1, then the output of the box will be a 1. If P coming into it is a 1, Q coming into the black box is a 0, then the output will be a 0. And then if P and Q are 1s, then the output will be a 1. So, looking at that, you're going, gosh, how do you figure that one out? Because that's not a truth table that really looks like it's not one of your standard truth tables. It certainly doesn't look like it anyway, especially because, you'd think, well, if it was a 0, 0, and a 0 here, and you had this one was a 1, well, you'd say that's an OR gate. That's simple enough. But these are actually reverse on an OR gate, so it's not quite as simple as you can see. This is the K-map, and the way we construct it is not P, P, Q, not Q, Q. So those are the 2 variables, the 2 inputs to this deal, and the result, or F, is inside the box. So when P is not and Q is not, that means that when P is a 0 and Q is a 0, the result is a 1. So you see that? 0, 0 is a 1. So if not P, true Q, not P, and Q is a 1, then the output's a 1, so we put a 1 right there. If P is true and Q is not true, the result is if P is true and Q is not true, then the result is a 0, so we put a 0 here. And then if P is true and Q are true, we get a 1. So that's our table. Now, so we're thinking, well, how did he simplify that to just P not ORed with Q? That doesn't really make any sense, does it? Well, it does if you look at this and you circle these. If you circle these 1s, this is the pair. These are called pairs when they're sitting next to each other like this. You can't go this way. You can only go this way or this way. But when you put these 2 together, what you're left with is not P, because not Q and Q cancel out. And then you OR it, and then here you're left with just Q, P and not P, and then these 2 cancel out, so you're left with Q. And that's exactly how K-maps work. There you have pairs, quads, and octets. You have 2 1s together, you have 4 1s together, or you have 8 1s together, and you circle these different pairs, quads, and octets, and by circling them, by inspection after putting them in the map, you can simply derive the equation. So here again, we've taken this truth symbol, and we came up with a K-map, and we said that's the solution, not P ORed with Q. So we're going to prove this by creating a ladder logic diagram and go through the truth table. So here we have not P is ORed with Q. Simple enough. So let's see if it's true. If P is a 0, that means this is off, then that's on. That's true. Doesn't matter what Q is doing here. If P is off and 1 is on, it doesn't matter either. Both of them are going to actually turn it on. So if P is a 1 and Q is a 0, well, then this changes states. If this is a 1, it's on. This opens. And this is Q is a 0 here. So this is a 0, and then obviously if this is on, then this is open, but Q is a 1, so it's closed, and then this is on as well. Okay, now we have another make the following K map into a truth table. So now we're going the opposite direction. So we have a K map given to us, and we need to figure out the truth table. So this is not A, not B, not C. So we have A, B, C are the inputs, and F is the output. So we have 0, 0, 0, 0, 0, 0, and the result is a 0. Next we have 0, because you can see here 0, 0, 1. So we're looking for a 0. So we're going to look at this column first. This whole column right here is this whole column right here. And this whole column right here is this one right here, because when A is a 1, this is all 1s. And when A is a 0, these are all 0s. So the next one we're looking for is B naught C. B naught C is a 1, so we put a 1 right there. Then we're looking for B not C. B not C is this one, so we put a 1 right there. BC, BC, it's a 0, so we put a 0 right there. And it's important that you understand this. We have not B not C, not BC, BC, B not C. You have to put it in this order for this to work. And that's kind of a hard thing to remember, because in your mind you're thinking that maybe it should be, you know, not B, not C, not B, C, B, not C, B, C, because that's kind of like how binary counts, right? But you have to reverse the last two. So if you continue this, you'll actually build the entire logic. We'll look at this one. 1, not C, not B is a 1. So these two, that's a 1 right there. And then we have a 1 here, and then we have not BC. Not BC is a 1. So there's your 1 right there. And you have B not C. B not C is a 0. So there's a 0 right there. And then BC, both being true, you have a 1 output. So there's your 1 output. So you can take a K map and convert it right into a truth table. But taking a truth table and directly converting that into a ladder logic diagram or into a AND OR gates is not an easy task. What are the 3 methods you can use to search in RSLogix 5000? And again, we covered this. You go to your menu and you type in, you know, up at the top of the menu in RSLogix, you slide over to the search, and then you can do Control F. You can do Go To, Control G. You can do Cross Reference, Control E. And you can also go into the search functions and the monitor to the tags and things of that nature as well. If you want to add a sub instruction, how do you do this? What is a sub instruction? So here I actually kind of set you up because I haven't covered sub instruction, but if you practice your course number 1 and course number 2, you should have been able to do this. You should have been able to figure this out. A sub instruction is a subtraction instruction. We're actually going to cover this in this course, but with the training you have had to date, you should have figured the following out. 1, create a new rung and type in sub. That would have given you your sub instruction. And then while you were on it, you could have hit F1, and that would have given you your help menu on that. 2, you go to the instruction menu and add a sub instruction. So we'll look at those. Step 1, add a rung. So you are in the ladder Logix. You go to this symbol right here in your favorites, and that pops in a new rung. And then while you're on your new rung, just type in sub and then hit enter, and your new instruction just pops in, right? So the sub instruction drops on the new rung, and there it is. So it's nothing more than a subtraction. You're taking source A minus source B and then storing it in the destination. An alternate method of finding this is you could have find the sub instruction in the instruction help toolbar. So if you would have scrolled over on that help toolbar, you would have come up to compute math, and then from the compute math instruction, this is your favorites right here, but when you clicked it, it would have popped up with the new compute math instructions, and there's your sub instruction right there. Click on the sub instruction, and it should drop right on in. There it is. So it would have dropped right in for you. And then obviously, if you're on top of this instruction right here and you click F1, then it'll pop up and give you the help menu on what that instruction is and what different types of words you can use on it, etc. Make a ladder logic program that will turn on out : 0/0 when I : 0/0 turns on and a delay of 10 seconds has occurred. Use both the Logix simulator and the RSLogix software. There's two tricky things with this. First thing is out : 0/0 is not a legitimate address scheme used in ControlLogix, right? That's an RSLogix 500 address scheme. So you know that you can, type in your input or your output any way you want. So that's what I did. I said I : 0/0 is input _0. And then we've learned in previous courses in RSLogix 5000, we can alias this to the slot 0, bit 0, and we would have, if it was in the local rack, we'd have local, and we've gone through that before, but we'll probably touch on that later as well. Let's see, then the output here, out : 0/0 is right here. I've made that just out _0. And then I said, make this turn on when this turns on and a delay of 10 seconds. So we added a time delay on, and this is in 1/1000th of a second. And remember, RSLogix 5000, you have 0.001, 0.01, and 1 second timers. But in ControlLogix, you only have 1/1000th of a second timer options. So your preset would have to be 10,000 to be 10 seconds. So what would happen is this would close. This would start accumulating up to 10 seconds, or 10,000 in this case, 10,000 thousandths of a second. When it was done, this bit would turn on right here. This would turn on, and the light would turn on, and the output would turn on. Now, using the Logix simulator, one of the gentlemen called me, and he asked me about the Logix and how he could simulate some of this Logix. And basically what you do is you go to that plc.net, I believe it is, or type in Logix in Google, and you'll get a 45 to 15 day free user pass to download Logix simulators. And it looks just like, well, it's fairly close, but it looks pretty good. And you can actually take the code that you've written in your 90-day free version of RSLogix 5000 and just drag it right into this Logix simulator, and it'll work. You can also do that with the 10-point MicroLogix RSLogix 500 program as well, and you can actually start playing with some of these simulators. So it's pretty straightforward. Create a ladder logic program that is an hour meter. Display hours in N:1, minutes in N:2, and seconds in N7:3. What is the maximum hours that can be displayed in the hour meter? How can this hour meter display 99999 hours? Well, that's a long time. Couple of things about this problem. Again, you see N7:1 is a SLIC 500 or RSLogix 500 addressing scheme, but I just used N7_1. And these can't, unlike the RSLogix integer values that can go up to only, the RSLogix 500 integer values can go up to 32767. The integer values, or double integer values here, can go up very high. So making a elapsed time meter in RSLogix 5000 ControlLogix is a lot easier. So here I created a retentive timer on. When the run turns on, this bit turns on, this retentive timer turns on, and it's a 1 second timer. When it times out, it turns this bit on, which resets that 1 second timer and increments this counter up by 1. Okay? So now we've counted 1 second. So when this counter here gets up to 60, it will be 1 minute. So this will continue. This little rung will just continue counting till it gets up to 60, and then it'll increment, and then we'll reset it. So when this guy's done, oops, did I go too far? Yeah, when this guy right here is done, then I reset the 1 second timer, and then I increment the 1 hour counter. And then obviously these are counting in minutes, and if you have 60 minutes, you have 1 hour. So this counter right here will count 1 hour. Whenever this is done, then I'll reset that minute counter right there. Whenever this one is done, then 1 hour has elapsed. So we'll increment our elapsed time hour meter, elapsed hour. So we didn't even bother with the N7. Maybe we did. We'll see. Let's see what we did. And then when the 1 hour counter is done, we reset it. And when the elapsed hour timer is done, we reset the elapsed time hour meter. And then I moved it over for you. Oh, I did do alias. So 1 second timer dot accumulate. So that was at the top. The accumulated value of the 1 second timer would go in there. So we'll just move it into seconds to OIT. And we did an alias N7 in brackets 3. So it's not :3, it's N7 in brackets 3. And we covered that in detail in course number 2, I believe. Probably even one portion, a portion of that as well. Then we took the 1 minute counter and we moved that into the minutes. And then we took the elapsed hour dot accumulation and moved it into the hours. Typically, I don't display seconds and minutes. I only display the hours. So it's not necessary. And you might play with this code because that might ought to say 1 hour counter, but you can play with it and go through it as well. So you can kind of go through this code a little slower. Stop your TV, play this in a regular DVD, and then write this code, and then carry on to the next lines and write that code. And you might come up with a dozen different ways to do this, a dozen better ways to do this. This is just one way. It's not tied to the internal clock, so it's not a very accurate way of doing elapsed hours. But for the most people in the world, if they know that their motor ran for 4,000 hours, that gives them heads up, that it's time to do some maintenance. Whether it's off a minute or so, I don't think they really care. And if it's real critical, then you need to do something better this and start using real-time clocks. Okay, so now I pointed you in the direction of the videos on the web. This is really important. There's a lot of free stuff Alan Bradley has given us on RSLogix 5000. It's really rare that they even do this. I can't believe they even put it out there. And if you look on your homework sheet, you'll see the actual addresses. And if you haven't done so, stop right now, close this, and go watch all those videos. They're excellent. It'll take you some time, but you should step through every single one of them. I don't know why Alan Bradley didn't do this for the slick stuff, but they've done an excellent job for the RSLogix 5000. And then I asked you, how do you get the help file in RSLogix 5000? And obviously you can press F1 on an instruction, or you can go to the help screen at the top. If you just slide over to the help screen and you can click it. So here we are. You can actually click it, the help screen, and it'll pop up your help menu, your drop down menu, and we covered that in detail as well. And then you can go instruction, let's see, it gives you contents, instruction help, release notes, online books, vendor project, sample projects, quick tour tutorial, we went over that, and then the tip of the day. And the tip of the day turns on every time you turn on your RSLogix 5000 program. Design an RSLogix 5000 program that uses the following instructions: an equal to, an MCR, which is a master control reset, a CMP, which is a compare, and then a TND, a temporary end. Make a light turn on if the valve if the value of a tank equals 100%, only run this code if a input underscore 1 is true. So here I just made up some program. This is kind of what people tell you too. Process engineers will sit there and tell you these kind of things. They'll try to write it up in a description or control philosophy, and then you've got to decipher the English language or whatever it is you're reading into PLC code. And again, I'm not a big fan of these master control resets, but I did it anyway. So here we have input 1 turns on, and if you recall, what's inside the master control reset is not running until this input 1 is on. So if input 1 is not on, then none of these output instructions, the light will not turn on, and it'll just jump from 0 to 5, which is a temporary end. Now this is kind of silly because what do we have here? We have a continuous loop, and you'll find out later that when you do that, this thing will fault on a watchdog timer if you have a temporary end like this, because it has no way to get to the end instruction. So that's not a good design here, but it'll run for a while anyway. So here again, whenever this is on, we take the value, the new tank value, and move it into tank. And then we take the tank level and we move it into tank level just so we can see it. And then we take, if tank is greater than tank level, turn the light on. Okay, so now what we've done is we've actually gone into a RSLogix 5000 program on this homework number 18 problem. And so you can see that this input is not on. So when we slide down, you can see the light is not on. Now you can see here, new tank value here is 125, so that moves into 125 here. So that says tank value is 125. And tank level is 100. So tank is actually greater than tank level. The light should be on. Okay. So here, let's toggle this bit. And now once it's toggled, the light turns on. See that? So let's go here and type in 75% let's say. And you can see immediately that light turns off. We can put in, 110, and the light should turn on. See, the light turned on. So that's how that instruction works. Now, I don't know why it hadn't crashed on us, because that temporary end is in an odd place. Again, I'm not a big fan of these master control reset programs or these temporary ends. I try to keep it real simple. I think it's the best way to do it, but you can play with it, and hopefully you don't get into trouble with these master control resets and temporary end instructions. And again, using that help screen up here, you can click help, and you can see the contents, the instruction help, the release notes, the online books, the vendor sample projects, the quick tutorial, the tip of the day, and about RSLogix, your serial number, and what have you. Okay, the next problem, I guess that's problem number 19, is design a PLC that uses a 1756L61 CPU, a 7-slot rack, 2 1756 IB16 cards, 1 1756 OW16 card, and then 1 1756 IF16 card, and 1 1756 OF4 card. The power supply will be powered by 120 volts AC. Find the schematics for each card, and then configure the PLC in RSLogix 5000. So going on the online manuals, you should have been able to find all these cards, and an easy way to do it obviously is to just type in Google, go to Google and type in 1756-L61, and there you'll have it. You'll have all your cards and all your information. So we'll go through this process. The first item is your L61 CPU, and again we covered this in the first course, I believe. these particular topics here. And just one of the things I want to talk about here real quickly is that battery. I know I mentioned it before, but the battery needs to be changed quite a bit. So what you need is a good battery. If you have the L61, it doesn't run out of memory as quick as the 55 controllers. The 55 controllers, if you've got that little bitty battery right here, you can see this battery's right, let's see, right here, okay? If you've got that little bitty battery right there, it will die within 40 days or something crazy. You have to put the larger battery pack in there, and then that'll last for, I can't remember exactly what it is. I think it's in the slides here. But make sure that when you buy these that you go ahead and upgrade to the L61. It's actually cheaper than the 55 controllers, so it's actually a good thing. You'll need a programming cable, a CP3 cable, and that's how you can download this processor. Okay, next